Okay, so I'm gonna present something which grew out of the whole GC proposal thing. And this actually turned into a paper I'm gonna present at Uppsala in 2 weeks. So this is kind of like a pre-run of the talk some version I will give there. And just to give a heads up warning, you will mainly see type theory and lambda calculus, not so much Wasm here. So this is more like real research or a real research presentation. Okay, so let's get started. The Wasm GC extension, which finally ended. One thing that was complex about it was actually not so much the operational semantics, but how do we type that stuff, right? So we want to avoid having runtime type checks when we access objects like other VMs do. So we want to have a sufficiently precise type system. And to make that working, you need the ability to define mutual recursive types. And you saw an example yesterday in one of my slides for encoding classes, for example. I think I have a similar one here. So if you want to, like in some pseudo code OO language, for example, you want to encode this class, what this has to lower to is a bunch of types. So you have an instance type, which has the variables, the instance variables here, but also a pointer to the V table, which is the method dispatch table. That's the standard way how you compile such languages. That V table or method table is another struct, which has pointers to all the methods, like code for the methods. And the methods themselves are usually defined or compiled, and I only show F here, by adding an additional argument to the argument list that is explicit, which is the implicit receiver object itself. So that is mutual. So all these types are mutually recursive. It's just one example where you need that. Yeah, I hope nobody is surprised by seeing this. So there are two main semantics for recursive types. One is called Equi-recursive, the other is called Iso-Recursive. So what's the difference? So Equi-recursive types are like a largest fixed point interpretation. So basically, when you have these kind of type equations you saw on the previous slide, you just assume they are recursive, and I take the greatest fixed point of what is valid according to that. So that is a co-inductive interpretation, in case you care about that. And it also means that usually the recursion is left implicit, right? I just have these equations and I have the most permissive interpretation of that, essentially. So that means that it's kind of like a nice semantics because it's kind of like the most permissive one you can possibly define. It's the largest fixed point. In that sense, it's a sort of canonical choice. But it has a number of drawbacks. In particular, so meta theory is somewhat more complicated, but for the Wasm use case, one problem in particular is also that the algorithmic complexity is not really what you want, because what this interpretation means is that every type is like equivalent to an arbitrary number of its unrollings, right? And that is kind of implicit in all the type equality. So all sorts of algorithms that operate on types, like type equivalence or subtyping, have to always take that into account. And that there's literature about that, blah, blah, blah. I don't want to like bore you with details, but it kind of means that all these algorithms are sort of equivalent to algorithms on deterministic finite automatons. And they are like definitely not linear. Okay, so this is a bit annoying, and it's not like we didn't try. We tried to do this, but it was too expensive, definitely. So the idea was to fall back to iso-recursive types. So what does that mean? They are like basically the smallest fixed point. Usually, although you don't have to, you make the recursion explicit. You could also infer it, but some languages do that. But usually, like at some point, it is basically explicit and fixed. And this is an inductive semantics, which means that all your algorithms can work in a bottom-up fashion. So that makes it much more pleasant to work with. But of course, it's also less permissive, right? Because it's the smallest fixed point. But as a side note, there's a very interesting result, which is that the expressiveness is actually equivalent to Equi-recursive if you're willing to insert all sorts of coercion functions that you synthesize. So wherever you would use Equi-recursive subsumption, so this is about Equi-recursive equivalence, you would have to insert a coercion function. And these functions, of course, can be operationally expensive because they might have to do deep copies of arbitrary large things, right? So at least if you do it naively, that's not particularly useful, but you could build that into a type system and get away with it. And the nice thing now is that these algorithms we care about are like quasi-linear. They're not really entirely linear depending on various details, but for like in the first approximation, because they're just bottom up, you can view them as linear. So that's kind of where we wanted to go. And as a running example here, let me pick something that's a bit simpler than classes, so just structs. So if you have a recursive struct like that, you would lower that to an iso-recursive type like this. So this is the syntax for iso-recursive types. And the point here is it's no longer like an equation where the left-hand side can occur on the right-hand side like before, but it's actually a closed form, right? And you have this new form binder, this new binder, which is the usual syntax for recursion binder, that binds an auxiliary type variable that allows this type to refer to itself. The point is it's a closed form on the right-hand side. So that's why it's a closed term, and we can talk about it in an inductive way. So let's simplify that example further, but extend it in another way. So let's talk about mutual recursion, where we have two structs. And this one refers to D, and this one refers to C, back to C. So what happens now? Well, if we try to lower that as before, it looks like this. And here, this isn't actually recursive with itself. It's just referring to D. So alpha C doesn't really occur there. And if we just do independently the same with D, well, we end up with D actually is recursive, but it also refers to C. But now we are back to where we started. We have two equations that refer to each other. So we haven't really solved the problem, right? So we have to do something about that. We have to transform that in some way. So we have to, first of all, identify groups of mutual recursive types, and then we have to somehow make them closed in the right way. So these recursive occurrences there, we somehow have to change them into something else. And the way to do that is, well, basically you substitute one into the other. So you sequentialize them somehow, and then you substitute here. And where you previously had a C here, you're now referring to that alpha C here. So this is again like a closed form now. And this is also a closed form because you can now take this C thing and just substitute it in here. Does that make sense so far? Okay. So basically the idea is you break the mutual recursion by expanding all forward occurrences. So that looks reasonable in this small example, but unfortunately it doesn't scale well. And there's another thing that's related to that I should point out. Like the occurrence here that we substitute because we changed C into this variable, it's not the same type as this one. It's actually a different type, syntactically, right? And that becomes a problem when we have more than two. So here's an example with three types, kind of a similar structure, just extended to three types. So you would now first naively have these equations, and now you want to make them all closed. So starting, because those are all like forward occurrences. So let's start with the last one. You substitute the C in B by putting that in there. And then we have to substitute the B and C and A as well. So to substitute the B, we now have to substitute the entire thing that is B now. So it becomes this. And similarly with C, we have to do something like this. And when you think that to its logical conclusion, you realize this is actually exponential in the number of types that occur in the mutual recursion. And so this is all semantically fine, but in terms of complexity, you're kind of like, okay, we have a nice linear semantics now, but actually the encoding we have to do is exponential, so that doesn't really help us, right? So we have to fix that somehow. And I mean, we're not the first to run into this. The one folklore solution to this is to extend the mu operator, so this fixed point operator on types, to what's called higher kinds. So don't worry exactly what that means. In this case, we only need something relatively simple, which is tuples on the type level. So the idea is you introduce something like type tuples. So these are not tuple types, but tuples of types, right? And then you can have this mu operator, and the variable is of a kind. So a kind is the type of a type that is itself a tuple. And this allows you to basically have one mu that defines multiple types, mutual recursive types in one go. And as I said, it's a folklore solution. For example, it has been used in the formalization of standard ML like 20 plus years ago. So what it would look like here is we would just define one recursive type, which is all of ABC together. So all of them are like in this, and this alpha now becomes a tuple. So like if we want to refer to one of components of the tuple, we have to project the right type out. So inside here, alpha dot one is essentially A. So does that make sense? And then A, B, and C itself, you can just define as the projections of these types. So, and that solves our problem. So this is now a linear sized encoding, all nice, and it works. So is our problem solved? Well, it is, until we add subtyping. And the thing I was surprised to actually realize, because I was not aware of this, is that this encoding doesn't scale to subtyping, and there's nothing in literature that talks about that. It's always kind of assumed like, yeah, it can just do that. Why does that not work? So let's pick a somewhat different example. So a tree represented as a mutual recursion between a tree and a forest. So it's a tree of arbitrary span, arbitrary branching. So the children of the tree are a forest. So the forest is just a set or a list of trees, essentially. And here I represent it as a linked list, right? So every forest structure has one tree and then the next pointer to. And I kind of assume here we have null pointers just to simplify the example. So if we lower that the way we did before, it becomes something like this. So the first int there is just the label on the nodes, and tree and forest are the first and second projection of that thing. But we have subtyping, right? And according to, like, for example, in OO, according to object-oriented ideology, I should, of course, be able to define a subtype of tree, let's say one that adds an explicit count for the size of the tree it's representing. So if we lower that now, using what we did before, it's actually not even recursive, right? We just like get this. So I write the mu here anyway, just for consistency, but it's just like this plain tuple. So I write in braces here, like records, but it's basically a tuple. So that is not recursive. It looks harmless as is, but the problem is, what we also need is that this thing is actually a subtype of tree. Right? And how do we establish that? There's no way to actually establish that. At least not using standard type theory, because to understand that, we have to look at how subtyping is defined on these kind of constructs. So first of all, the usual rule for subtyping on mu types is that they are, one is a subtype of the other if their bodies are in a subtype relation, assuming the variables. That's the so-called Ember rule, because it was first used back in the 80s in an experimental language by Cardelli called Ember, but it's kind of the standard rule being used. And for these type tuples, well, subtyping is very straightforward. It's really just point-wise, element-wise. You could also add width subtyping on these tuples, but spoiler, that doesn't actually solve our problem. So here we require that they have the same arity. And if you go back to this example, that means there's no way this thing can be a subtype of that because it doesn't even have the same shape, right? Like they're basically completely unrelated by these rules. So that doesn't hold, unfortunately. And there's no way to make it hold in this setup, really. So there are various generalizations, or not various, a number of generalizations that you find in literature to iso-recursion that tries to make it more expressive. One is Ligeti et al. A couple of years ago. They changed the subtyping rules so that you compare the bodies not with the assumption that A is a subtype of alpha is a subtype of beta, but you actually substitute them. So you basically unroll ones in the subtyping. That's a bit ad hoc, and it's actually the case that 20 years earlier there was already a suggestion to have that as a general rule that doesn't just apply in a specific place in the subtyping rule, but that you can just unroll any mu type once and it's an equivalent type. It's called Shaw's equation sometimes, and this came up interestingly in the context of module systems and type abstraction. Now, the problem with these generalizations is that they're actually co-inductive, right? Because if you look at this equivalence, it's really like the usual unrolling rule for equi-recursive types, except that we keep the mu here. But other than that, you have all the same problems. And this is just an instance of that as well. So it doesn't really, like, it basically throws the baby out with the bathwater. It brings us back into this territory we don't want to be in. So what do we do? So the thing that I proposed was to kind of get away from this idea that we make the subtyping relation stronger, which is kind of like we want to make the use side of subtyping stronger, which kind of always means you want to infer something or more, like what is the subtype of each other, right? You need a stronger inference, and that usually comes with more complexity. What if we look at the definition side instead? So that the user, or the, in our case, more like the producer, has to declare what subtyping they want. So the core idea is to do exactly that, and this whole work is about identifying like a minimal extension to the standard type theory that does exactly that. And the minimal extension is that we, instead of having this mu binder, we have this thing, which has a bound on it. And that is a very, at first sight, is a very natural extension, because the same kind of thing you have with other binders when you have subtyping in lambda calculus, like for alls and exists, they all usually have this kind of bound. And now we're just like transferring it to mu. But okay, what does that mean now, right? So what are the subtyping rules? So first of all, well, you have the usual reflexivity and transitivity rules. So we assume those are given. They always exist for subtyping. Sometimes they are kind of explicit rules. Sometimes you can prove them as admissible. I assume here they're explicit because that is the somewhat simpler factorization. And then the subtyping rule for mu itself now becomes extremely simple. It just says the only direct supertype of such a mu is the thing we have declared here. That's it. And there are no other supertypes, well, except for itself, of course, according to this. So that always works. But obviously, this can't somehow, I mean, it seems like this holds vacuously, so that can't really be true. How do we ensure that this makes any sense? Well, we don't have just subtyping rules, we also have well-formatness rules for types, of course, and calculate like that. So the well-formatness rule for that now has to make sure that these are in proper relation. So it's like, when is a type like that okay to be written? And the first thing, of course, is, well, the body itself has to be okay. That's kind of like the obvious thing, assuming the bound is okay, and that implies actually that T1 is okay as well. And then the important part here is now that also T2 has to be a subtype of T1. More specifically, the unrolling of T1. And the unrolling is essentially the extracting the body of T1. So there are two cases. So either the T1 can just be top, so that's basically a type that doesn't have any interesting supertype, or it is another mu type And then the unrolling is like this usual substitution you have. So that's the, oh, sorry, this is actually typo. This should be U2, where you substitute the whole thing for the binder vector. So this is again like the body. So this thing has to be itself a mu type then, if it's not top, and you're taking the body of that where you have done a one level unrolling. Yeah. Yeah. This one.
Andreas, I was hoping you could actually use your cursor to point at things, because we can't. If you're pointing in the room, we don't know what you're pointing at. Thank you.
Okay. Yeah. Thank you for pointing that out.
I just had a minor clarification.
Yeah.
Presumably, you're just omitting part of the context to make the slides simpler.
Yeah.
You might have
context.
You may have other variables that also have bounds, right?
Okay. Making the rules more readable by omitting those parts of the context that are kind of parametric here. Okay, so this is the whole idea, really. And with that, we can now translate these two types into something like this. So it's the same as it's the same as before. The only thing that's changed is now that we have the bound here. And in this case, the bound is kind of trivial. It's just the two top types, because both these types don't have a super type, right? So the interesting thing happens here now, where we now say that, well, this thing is actually a subtype of tree. And with that, I mean, this relation trivially holds because we can just read it off here. We just declared it. But what the proof obligation we have now when we're checking this is that actually an okay definition for it, right? And there are two things we have to check. So the one was we first have to check that the body is okay, given like alpha is okay, although that doesn't even occur here. So that's kind of straightforward. It's just a tuple. And the more interesting part was checking the subtyping. For that, we first have to unroll the tree type, which amounts to the pair here. Oh, this is super slow with the cursor. Where alpha has been substituted by tree forest itself. So that's what you get here. Comes a bit lengthy, but we have also defined these abbreviations, so we can kind of shorten that to that. And at that point, we can apply type level reduction, because there's, of course, an equivalence. If you project the first component from a type tuple, then that's equivalent to that component of the tuple. So this becomes just this subtyping check, and that's just standard width subtyping, and that holds. And we are done showing the functions. So that's really the core idea. There's much more in the papers, and in particular, it extends this whole thing to higher order types. So type level lambdas and everything. You have higher order subtyping, and it shows how that allows you to encode parameterized types with blocking reduction. There's another extension. One thing I didn't show here is, so you can also have subtyping within a recursion group. And to be able to express that, you need a slight extension here. So the paper has the full calculus with soundness proofs, decidability proofs, and it makes the point that this is essentially looks like nominal subtyping, because you're declaring your type hierarchies. But it's still not nominal, because if you have the structurally same types twice, they are still like equivalent, right? So if you were to canonicalize all the types in your program, then it's basically what nominal subtyping is. So it kind of explains what nominal subtyping even is in a more like type theoretic fashion, if you want. And then also in the paper, I proved that you can encode the subtype emulation of Java, or like this Java calculus featherweight generic Java into that. And I explain how that applies to Wasm, and I identify especially a subset of this general higher order calculus that has only a notion of shallow reduction. So the problem with higher order types is, in general, you have to do arbitrary beta reduction to check for type equivalence, which means arbitrarily deep substitution. But you can actually define, specify a fragment of the full type language where all the substitutions you have to perform are shallow, so they are only like into type parameters. substituting type parameters, which is exactly what nominal languages with generics have to do. So again, it kind of shows where that is actually coming from, like that works. And yeah, that's going to be in 2 weeks. And that's all I wanted to show here, I think. Oh, there's future work. Yeah, there are a couple of things you could extend this with. So in the paper, there's like, I don't know, 40 pages of handwritten proofs for all these properties. But I'm collaborating with a guy named Stephen Keuchel, which some Googlers might remember. I don't know. He used to be an intern on the VA team, actually, long ago in 2011. He implemented lexical scoping for JavaScript. So we want to mechanize that in Cork, and he's mainly doing that. And then there are various extensions you can consider like multiple supertypes, F-bound, so recursive supertypes and stuff. But yeah, that's future work. So now I'm done.
Can you do about 4 minutes of questions?
I can take you, Mike. Is the mechanization work something that could be contributed to Wasm Cert Cork? Or is it mainly about the type system in the abstract?
Yeah, it's really on the lambda calculus level, so I don't know if you can easily transfer it. And actually, the hard part about it is I actually tried to tackle that myself, and then I realized nobody has ever like mechanized higher order subtyping at all, right? So the big part of this mechanization isn't actually this extension, it's about mechanizing F omega sub.
I mean, I'd love if whatever mechanization came out of that, even if it wasn't integrated, even if they didn't make an effort to integrate it, was in some form that we could take the proofs and integrate them instead of having to redo everything.
Yeah, that would be cool, but
Unlikely.
Knowing how Cork proofs work, I don't know if that's realistic. Yeah, but
maybe this is just me being slightly pedantic, but you suggested that somehow Equi-recursive types are greatest fixed points and Iso-recursive types are least fixed points. This is not true.
It's not true?
No, it's completely orthogonal. You can do co-inductive Iso-recursive types. You can do...
Yeah, okay, well, those are like the generalizations I showed, right? Which is not the usual interpretation of...
I'm just saying they're orthogonal concerns.
But what would be an inductive equi-recursive type? I don't see how that can... Okay, let's
You can do it mathematically anyway.
Okay.
One of the things that came up as a risk when we introduced this was the fact that right now there's only one supertype, and obviously there's future work to allow multiple supertypes. But you have to make sure it remains a lattice. Have you had any further thoughts about this limitation and its practical effects? It hasn't come up for any of our real world partners yet, but theoretically.
So far, I think Ben is the main person who would like to have that somehow.
It could be useful.
I mean, it's a much more general problem, right? Because if you do that, you implicitly introduce intersection types into your type system, and they usually make everything explode in terms of complexity. So the first problem to solve here is actually how maybe can we somehow delimit it in some way that does not lead to general type intersection? And I've thought about it a little bit, but I don't really have an answer. And that is even kind of independent of the rest of the mechanism in a way.
I'll just say the benefit is kind of minor because it only helps you type data.
The benefit of that's is pretty minor. It helps you type interfaces in Java, but it doesn't help you with interface dispatch. So it saves you some CAS on Java. That's about it.
Yeah, that's my feeling too, that this is kind of another one of these type system extensions we could consider, but it's probably maybe more complexity than it's worth. So unfortunately, there are quite a few of those. Okay. Hold on.
All right.